Hello everyone. Today we will see open loop system, loop gain system, and closed loop system. And we will check pole locations, bandwidth, unity gain frequency of all the system, and we will relate all these parameter to each of the system. So before we start, let's see impact of beta on stability. So in first rate curve, at unity gain frequency, we are getting a phase shift of minus 180 degree. Okay, here. So here phase margin is 0 degree. Now I have reduced the value of beta. Due to this reduction of beta, my gain crossover frequency or unity gain frequency reduces. Okay, so it will shift to the left side. After shifting left side, my phase margin here, you can see here, this much of phase margin improves. Okay, so after reducing beta, my phase margin is improved, so my system becomes more stable. And after increasing beta, my gain crossover frequency shifts to the right side and my phase margin is reduces, so my system becomes less stable. So I have written here, reducing beta reduces gain crossover frequency, system becomes more stable. And increasing beta increases gain crossover frequency and system becomes less stable. So beta is usually a frequency independent ratio of resistors. So we sense the output by a resistive divider networks. Okay, so usually you will see this type of network. So this is attenuator. So beta equal to R1 divided by R1 plus RF. Okay, so since it's a resistive network attenuated, so maximum value will be 1 and minimum value is 0. So minimum value of beta 0 means you are not sensing the output, you are not feeding back to the input. Okay, and if beta equal to 1 means you are taking all the input, all the output, and you are feeding back to the input to compare. So beta range is from 0 to 1. So maximum beta is 1, and minimum beta is 0. So and beta equal to 1, which configuration? It will be unity gain configuration. So maximum beta value is 1, and we saw here that increasing beta increases gain crossover frequency and system becomes less stable. So suppose your system is stable for maximum beta, then it will definitely be stable for less than some beta max. Okay, so I have written here, hence if system is stable for beta equal to 1, beta equal to 1 is maximum value of beta, then it will be stable for beta less than 1 also. Okay, so beta equal to 1 is the worst case for stability. So if your system is stable for beta equal to 1, so your system will be stable for beta less than 1 also. Okay, so now let's see the transfer functions. This is typical representation of a closed loop system. So here is open loop system. Okay, and we are sensing the output by a feedback network beta, and we are comparing, and this generates a error, and then it's again amplify, and then how you get output, and this goes on in loop. So open loop system is transfer function is this one, AOL as okay, and the loop gain transfer function is defined by beta times open loop transfer function, and closed loop transfer function is open loop system divided by 1 plus beta open loop transfer function. Okay, so this thing you already know. So let suppose, so we will examine for beta equal to 1. Okay, because that is worst case for stability. So let the open loop function is a single pole dominant differential amplifier. So here beta equal to 1. So how we will represent this one? Suppose this one single pole dominant differential amplifier. So I have made one. This is differential amplifier. I have taken this output and I have fed back to the input at negative terminal. Okay, so how to decide positive and negative terminal? If we increase this terminal, so this is common source, that will decrease, So that will decrease and that will increase. So increasing this increases output. So there is no inversion. So it's non-inverting terminal. So the other will be obviously a inverting terminal. And suppose I want a beta network. Okay, so I want some fraction of output to feed back to the input side. So how we will represent? We take the output RF and we feed back a part of the this output to the input side. So okay, so this is how we will represent. Now let's analyze the all system. So first let's consider open loop system. So it's a single pole system. So whose DC gain is ADC, pole location at omega p open loop. So Bode plot of this system will be ADC and it will start attenuate by 20 dB per decade at pole location. So what is pole location? Pole location or 3 dB bandwidth, these all are same name, okay? Because at when you put omega p equal to omega pol here, okay, so you will get ADC by root 2 and that is 3 dB. So ADC 1 by root 2, when you will calculate, it will come as 3 dB. So we say pole location as 3 dB bandwidth or pole location. Now we will calculate gain bandwidth product. So what is gain bandwidth product? It's your gain and first dominant pole. Okay, first dominant pole into DC gain is gain bandwidth product. So DC gain is ADC. First dominant pole is omega p OL. Okay, now we will calculate unity gain frequency. Unity gain frequency is where your magnitude drops to 1. So it's simply ADC by root over 1 plus omega u by omega p L square equal to 1. So I ignored this one. Okay. So after calculation, we will get ADC into omega p OL. So it's equal to the gain bandwidth. So for first order system, your unity gain frequency will be nothing but gain bandwidth product. Why I have calculated this separately? Because in two pole system, your gain bandwidth product will not be equal to the unity gain frequency. Okay, so I wanted to differentiate what is gain bandwidth product. It's a DC gain and first dominant pole frequency. Okay. Now the second thing is loop gain system. So loop gain system is beta time into open loop system. So beta into ADC divided by 1 plus S by omega POL. So here you can see the pole location is same as open loop system. So pole of loop gain system and pole of open loop system will be same. So I have marked this pole location of loop gain system. And DC gain is changed. So it became beta time ADC. So pole is same, DC gain is changed. So in this case, the gain bandwidth product will also change because DC is change. So pole is same, bandwidth. So bandwidth is also same because pole is only 3 dB bandwidth. So what will be the unity gain frequency? Again, beta A DC divided by 1 plus omega u divided by omega p OL is equal to 1. So we will ignore this one. So omega u of loop gain system will be beta times ADC into omega POL. It's also equal to the this whole term is gain bandwidth product of open loop system or unity gain frequency of open loop system. So your unity gain frequency of loop gain system becomes beta times unity gain frequency of open loop system. So here you can see unity gain frequency of loop gain system is beta times unity gain of open loop system. So many people say like your beta, your DC gain is decreasing, so your bandwidth will increase. So that's not the case. We are not moving on the same curve. This is different curve. Okay. If we will move on same curve, then your DC gain increasing, then your this bandwidth increasing. But this curve and that open loop system curve are different. We are moving on different curve, so that will not be the case. Here you don't say like you decrease your DC gain, so your bandwidth will increase. No, here bandwidth is constant. You decrease your DC gain, so your unity gain frequency will change. Now the third system is closed loop system. It's a open loop system divided by 1 plus beta into open loop system. So put the open loop system transfer function. Okay, after rearranging, so you can do, we will get ADC divided by 1 plus beta time ADC 1 plus S divided by 1 plus beta ADC and omega POL. So you see here DC gain change and pole location also change in closed loop system. So DC gain reduced by 1 plus beta ADC and the closed loop system increased by 1 plus beta time ADC. Okay, and here unity gain frequency is same as open loop system. So unity gain frequency of closed loop system and unity gain frequency of open loop system is same. So we will verify this one. Okay, so pole location, closed loop pole location increased, okay, by this amount. So bandwidth, pole location are same thing, so it will also increase. Okay, now closed loop unity gain frequency will be gain bandwidth closed loop frequency for single pole system. So gain bandwidth product ADC divided by 1 plus beta ADC. Bandwidth is nothing but pole location 1 plus beta time ADC. So this will cancel out. So unity gain frequency of closed loop system will be ADC time omega POL. Okay, ADC into omega POL. And this is nothing but gain bandwidth product of open loop system, or you can say unity gain frequency of open loop system. In this case, unity gain frequency of open loop and closed loop will be same. Okay, now in this case you can say, since open loop system and closed loop system have same unity gain frequency, so you are moving this straight line. So this straight line is common for open loop system and closed loop system. So now here you can say that gain bandwidth product is constant. So let's summarize. So here I have made one table. You won't get any confusion. So open loop system transfer function is ADC divided by 1 plus S by open loop pole. So this one will be beta time open loop system. This one open loop system divided by 1 plus beta time open loop system. So after rearranging, we will get this one. Okay. So pole location of this one will be omega POL. So pole location or 3 dB bandwidth or bandwidth are the same name. So this will be same. Loop gain system pole remains same. Okay. Now here you can see pole location change. So I have approximated, I have ignored one. So beta time ADC into omega POL. It's also equal to the beta times unity gain frequency of open loop system. Here you can say beta time unity gain frequency. Okay, so this one is equal. You have to go through by you also. Okay, so that's when you will do by yourself, then you will understand better. So, and what will be the gain bandwidth product or unity gain frequency same for the first order system. So omega POL into ADC gain bandwidth. Okay, so it's ADC omega POL. Here gain bandwidth beta time ADC into omega POL. Beta time ADC into omega POL. Here gain into bandwidth. So it will come ADC into omega POL. So you can check this one. Okay. Now I have plotted all curves on same. So this one is open loop system. Okay. And the red one is closed loop system. So this part is common for closed loop system and open loop system. Okay. So because the unity gain frequency is same and they are going by 20 dB per decade, so they must be coincide. Crossing point is same, slope is same, so it must be the same line. Okay, and this one is loop gain system. So in loop gain system, our pole is same. We decrease the DC gain, so my unity gain frequency also decreased. Okay, so now here we can see open unity gain frequency of loop gain system is beta times of unity gain frequency of open loop system, and closed loop pole is beta time ADC into open loop pole. Now here these are important relationships. Okay, so gain bandwidth product is nothing but unity gain frequency only in case of first order system. In second order system, when you will calculate gain bandwidth, it will be gain into first dominant pole, and it will roll off by 20 dB per decade. But when you will roll off, you will get another pole in between. Then your that line will tilt. Now what you had expected, that unity gain frequency, that will not be the exact unity gain frequency. So in that case, unity gain frequency will be less than gain bandwidth product. Okay. So usually in our design questions, they will give gain bandwidth product. So that gain bandwidth product is nothing but the open loop gain bandwidth product, and that is unity gain frequency of open loop system. So gain bandwidth product is unity gain frequency of open loop system. So, and we know that unity gain frequency of loop gain system is beta times unity gain of frequency of open loop system, and equal to bandwidth closed loop divided by beta. So if someone have given you gain bandwidth product and DC gain, so open loop bandwidth or pole location of closed loop, simply divide this gain bandwidth product divided by open loop DC gain, so you will get bandwidth, okay, of open loop system. And when you will divide this gain bandwidth divided by closed loop DC gain, so you will get bandwidth of closed loop, okay, or pole location of closed loop. Now, importance of unity gain frequency or gain bandwidth product. So here bandwidth of closed loop system is pole location of closed loop system, and it's 1 plus beta time ADC of pole location of open loop system. So approximately it will be beta time ADC open loop pole system. And this one is gain bandwidth product of open loop system or unity gain frequency of open loop system. So it's beta times unity gain frequency of open loop system. Now we know that beta equal to 1 is the worst case for stability. So at beta equal to 1, bandwidth of closed loop system is nothing but unity gain frequency of open loop system. So what they are giving you specification as unity gain frequency of open loop system is nothing but your closed loop bandwidth. Okay. So your open loop unity gain frequency becomes closed loop pole or closed loop bandwidth when it puts in unity feedback. Okay. So open loop unity gain frequency is closed loop bandwidth of your system at beta equal to 1. So here I have shown this thing in plot. This one is unity gain frequency of open loop system, and it will become bandwidth or pole location of your closed loop system at beta equal to 1. So that is the importance of your unity gain frequency. So these things are asked in interview very frequently, that why we calculate unity gain frequency of open loop system. So it's simply when you will put that system in feedback system, so that unity gain frequency is become bandwidth of your closed loop system. Okay, so I hope I was able to explain. Okay, so if you feel any doubt or you see anything wrong, please tell me. Okay, I will correct that one. And for second order system, gain bandwidth product will not be equal to the unity gain frequency. Okay, so simply suppose here you will see one more pole locations. So you calculated gain into bandwidth, you are supposed to cross here, but in between you get one pole, and now you are till down another 120 degree. So your unity gain frequency is exactly this one, but you had calculated this one. Okay, so in that case, your unity gain frequency will be lesser than gain bandwidth product. So in that case, we sometimes we define two gain bandwidth product. Okay, so when you will see data sheets, so I have seen some Texas Instrument data sheet. They define uh, two gain bandwidth product. For one frequency range, there will be one gain bandwidth product, and for other frequency range, there will be another gain bandwidth product. So you have to see which pole location you have to use for your designing the question. Are you considering your unity gain frequency as DC gain into first location, or you are considering your DC gain into second location, pole location? Okay, so it's simply completely depends upon your compensation. Are you able to make the system completely first order, or you will not be able to completely compensate to the first order? Okay, so okay, thank you. If you again you see any correction thing, then please let me know. I'm also learning. So okay, and thank you. Bye.